All right, we are back with the other solutions for the rest of the problems in the exponential worksheet. So let's go ahead and just continue. So in this problem here, we have a count in a culture of bacteria 600 after 2 hours and 20,000 after 6 hours. Find the relative growth rate. So we're going to use the growth rate formula here, change in ln of n over change in time. So we're going to have ln of, this is going to be n2 and this is going to be n1. So I'm going to have ln of natural log of 20,000 minus the natural log of 600 over 6 minus 2. Okay? Alright, so we did that in our calculator and it came out to be 0.876. So 0.8766. Okay? Find the initial bacteria count. So we know that n equals n sub 0 e to the 0.8766 t, because this is our formula for the exponential growth. We're looking for n of 0, so all we're going to do is we're going to use some of the information that they gave us. Looks like we could use maybe this one right here, 602 hours. So we're going to plug in 2 hours for t, and we're going to plug in 600 for n, and we're going to solve for n of 0. Okay, and then times 2. Then we're going to divide all of this stuff over. So n0 is going to be 600 divided by e to the 0.8766 times 2. And let's go ahead and calculate that. 600 divided by parentheses e to the 0.8766 times 2, 103.931. Okay, so 103.931. Now that we got that, we can go on to part C. Find the function that models the number of bacteria. Well, we've got pretty much everything we need. So n of t is equal to the initial, which we found right here, times e to the 0.8766 t. And, oops, sorry about that. And that would be our answer right there. Okay? All right. Move on. Oops, wrong way. All right, so now we're talking about radioactive decay. And I mentioned in a previous video about half-life. So you should have some idea about what half-life is. It's how long it takes to get half of what we have before. So our half-life is 8 days. We have, if t equals 0 and our amount, we'll say m, is 100, okay, that's m of 0, then how many days, or actually when t equals 8, we're going to have half as much as we started with. So this is going to be 50, okay? So we're going to be able to find what r is by using this information. So r is going to be the ln of 100 minus the natural log of 50 over 8 minus 0. Alright, so we'll do a quick calculation to see what that is. Alright, so looking at our calculator here, we get 0.08666. And now we want to know how long will it take for a 100 milligram sample to decay to a mass of 70. So what we have here is we're going to have 70 equals 100 times e to the 0.0866t. This is the formula n equals n sub 0 e to the rt. And I just plugged in r, and I plugged in n of 0, which was 100. So now we're going to solve this. You're going to divide 100. So you're going to have 7 tenths equals e to the 0.0866 time. And you're going to take the log of both sides. So we're going to have 0.0866 equals the natural log of 7 tenths. Oh, I forgot my time there. Then we're going to divide this number over, and we're going to have our time. So let's take a look at our calculator and see what that gives us. So when we plug this in our calculator, it turns out to be negative. Well, I would be suspicious on that because I don't have any negative time. So I must have made an error somewhere, and it turns out that I actually did make an error here. It should have been ln 50 minus ln of 100, 0 over 8. And actually it would have given us the same number. It would have just been negative, which makes sense because this is decay. And whenever we're dealing with decay, we're going to have a negative in that exponent there. So let's go and fix that. So here's a negative, and here's a negative. Here's a negative. And so the answer really should be positive 4.11. Looks like days. Okay, so that is the answer for that one. Let's go ahead and move on. Example number 5. If 250 milligrams of radioactive element decays to 200 milligrams, 48 hours, find the half-life. So we know that the rate is going to be equal to 200 ln natural log of 200 minus natural log of 250 divided by 48 minus 0. So we'll go ahead and do the math there and see what that comes out to be. All right, put in that calculator, and it gives us negative 0.0046. So our formula here is going to be n of t is equal to 200 e to the negative 0.0046 times t, and t is in hours in this case. So we want to know how long does it take to, find the half-life. So half-life means how long is it going to take to get 100 instead of, we started at 200, actually we started at 250. So the question is, how long is it going to take to get from 200 and what's half of 250? Half of 250 is 125. Okay, so really we're looking at 125 equals 250 e to the negative 0.0046t. So I'm going to divide by 250. And I'm going to take the ln of both sides. And I'm going to divide by 0.0046. And I'm going to get a time of 150.68 hours. All right. Okay, so let's keep going. Minimize that. All right, now we have Newton's law of cooling. Newton's law of cooling is something we use we can use in physics when we talk about temperature. And let's go and do this problem here, example number 6. So this stands for the temperature of the surrounding. This is the initial temperature of the object. So the thermometer is reading 72 Fahrenheit, is placed in a refrigerator. So this is our initial temperature, where the temperature is a constant 38 degrees. That's the surrounding. Okay, so the refrigerator is the surrounding temperature. After 2 minutes, the thermostat reads 60 degrees Fahrenheit. What does the thermostat read after 7 minutes? So let's first plug in what we know. So we know that 38 is our surrounding, plus the initial of 72, minus the surrounding, which is 38, e to the negative kt. So let's simplify this down a little bit. So we'll have 38 plus 72 minus 38, which is 34, e to the negative kt. So we are going to need to find, we're going to need to find k, and we're going to need to find t. So actually we don't need to find t because t is going to be given to us in the second part. But we're going to need to find k, and that's what this information here is going to help us find. So after 2 minutes, we're going to put 2 minutes in for t, and then we're going to put in 60 degrees for t of t, which is y. Okay, so we're going to have 60 degrees is equal to 38 plus 34 e to the negative 2k, because I'm putting 2 in for t. Oops, 2k. Alright, so I need to find what k is, or r. So I'm going to subtract 38 from both sides. And I'm going to get 22 equals 34 e to the negative 2k. Divide by 34. So 22 over 34 equals e to the negative 2k. And then I'm going to take the ln. So I'm going to have ln of 22 over 34 is equal to negative 2k. And so k is ln of 22 over 34 divided by negative 2. And we will estimate that in our calculator. So we'll go over to our calculator. And we get for k 0.218. And now we're going to use this formula to plug in t. So we're going to need to, I'm going to clear some of this stuff out so that we could, okay, 38 plus 34. All right, so we had t of t was 38 plus 34 e to the negative kt, and we're going to plug in our k. So there's our model. Now we can use this model to answer our last question. What does the thermometer read after 7 minutes? So we're going to plug 7 in for t. Alright, so we're doing t of 7. It's 38 plus 34 e to the negative 0.218 times 7. And we'll go ahead and calculate that now. And we're going to get 45.39 degrees Fahrenheit. Alright, so that's Newton's law of cooling. Alright, so that should be pretty much enough for this worksheet. I know that there are a few other problems on down below on logistic growth models, but really we're just looking at, oh, actually we can go and answer example 7. So let's go and do that. I think I have enough time. I can do this in 30 seconds. What is the carrying capacity? Well, that's easy. We just put 500. What is the growth rate? The growth rate is right here. So negative 0.162. And when will the population be 300 eagles? We plug 300 into P of t, and we solve for time. Okay? All right. So that's pretty much it for this worksheet. And there was one other thing on here, but you guys can just take a look at what's happening as we compare. Okay? And what are the changes. All right. So we'll see you soon.